Okay, so I want to also go through some examples of completing the square. And, again, something that is going to actually be really useful, not just this class, but as you move on throughout the rest of your experience going into calculus. It's something that I think just so useful in helping us analyze, but obviously, especially this year. And so that's why I want to just remind you and revisit this. Completing the square, I think we even did one in the last example, kind of isolate or sort of like temporarily ignore that constant term. So you're going to think of it as like y equals x squared minus 10x, and then leave some space and leave the plus 27 there. Okay, now our goal is to complete the square here in terms of picking a value that that we could add, so that when this much of it is factored, it's a perfect square. And you want the same number, so that's the whole idea of the square. And remember that number doubled is always sitting here. So an easy way to do that is divide that by 2 and then square it. And because you're squaring, this is always going to be a positive value. Regardless of the sign here, this is always positive. And so then, so I've added 25. So I'm going to immediately subtract 25. And that means my net change is 0. And I can add 0. Right? I'm adding 0 to this. And that makes that, that makes it not changing the problem. Okay. So now, I'm going to go back here. And so I'm going to factor this is y equals, and that's x minus 5 squared. And then 27 minus 5 is 2. So then there's my vertex form. And if I had to pick out the vertex, I know that it is 5, 2. Which is nice. Okay. Now, the next equation is x equals, and it's okay. Don't panic. You still complete the square by the same process, isolating your constant term. So it's just x equals. So then it's y squared plus 4y. Leave a little space, and then the minus 3 we're going to push here. And so again, we think, okay, what could I add here to make that a perfect square? So again, half of that number is 2. 2 squared is 4. So then we immediately subtract the 4 there. So we factor the first 3 components. So x equals quantity y plus 2 squared, and then negative 3 minus 4 is negative 7. Now be very careful if I asked you what's the vertex, because even though it's x equals, the x and the y still are the same positions in terms of naming a point. So the vertex is actually negative 7, negative 2, because this negative 2 is a y component that makes that value equal to 0. And then the negative 7, which is here, is an x component. So we put that there. So it's still x comma y. It's just that it appears differently in the actual equation because it's a parabola that's not a function. Okay. Now, the next example, we need to deal with that coefficient of a 3 in front. And so when I isolate this 31, that's fine. But I'm going to factor the 3 out because we know that 3 means my parabola is opening 3 times skinnier, right? 3 times faster is a rate of increase. But in terms of vertex form, it would have been factored out. So I need to factor that 3 out. And this plus 31 we can isolate over here is fine. But because we took out a 3 out of the x squared term, and we're also going to be taking a 3 out of 18x, so that's plus 6x. So that's, again, check your math. Like that's 3x squared plus 18x. So I did that correctly. So it's just here, just in the parentheses, that we need to complete the square. And again, we've seen the pattern. Half of 6 is 3. 3 squared is equal to 9. So I'm going to add a plus 9 here. Now, we might just initially or kind of blindly, without thinking, say, oh, then we subtract 9. Okay, but that's wrong, right? We're not going to do that because that's not technically balanced. It's deceiving, right? This is not a 9. This is actually a 27, right? It's a 3 times 9. It's a 27 in disguise. So what I need to do is erase this minus 9 because that's not adding it to a net change of 0. We actually need to subtract 27. So this 9 is in disguise as a 27 because it's modified by the 3. There's the minus 27. That's a net change of 0. So then I can go ahead and say, okay, so that's y equals 3x plus 3 squared. And then 31 minus 27 is 4. So my vertex is negative 3, comma 4. And again, this coefficient of 3 just means that the rate of increase is 3 times greater, making our parabola 3 times skinnier. And I know skinnier is not really a mathematical term. Maybe we could talk about it being vertically stretched, horizontally compressed. Okay, you could do exercise D if you want on your own and pause and see how you did or follow along. F of x equals, so remember that's just like y equals negative, so I know that's opening down. But again, there's a coefficient in front, so I'll call it y equals. So we factor out the negative 1/2 out of the x squared term. We'll also factor it out of the x term. We push the 7 out. We don't have to worry about factoring that out. Now be careful. When you divide by this negative 1/2, you're technically multiplying by its reciprocal. So what actually goes here is a plus 12x. And the checking is, I think, so much easier because you check, negative half of 12. Oh yeah, that's negative 6, and that's what we started with. Okay, so then we do half of that value. Half of 12 is 6, and 6 squared is 36. But remember, it's not a real 36 we're adding. This 36 is in disguise because the 36 is also under the influence of that negative 1/2. So that actually is a negative 18, right? You've just added a fancy negative 18 here. So now we have to counterbalance that with a positive 18 like that. So this 18 and the negative 18 cancel, so it's a value of 0. And that's what we want, a net change of 0. And then we group this, negative 1/2, and that's x plus 6 squared, and then 7 plus 18 is plus 25. So now our vertex, had we needed to label it, is negative 6, comma 25. And again, this coefficient in front of negative 1/2 tells me my parabola is opening down, and it's increasing at a rate half of what the normal increase is, making it a wider parabola, or vertically compressed, horizontally stretched. Okay. And then, excellent. So we have another example here. This is a piecewise function. And it's a piecewise function because depending on which x's you choose, like in the domain, you will have a different piece of the graph, right? A different image. So the transition point, it looks like, is negative 1. And so, and notice negative 1, although defined in both definitions, it truly belongs to the bottom function. And that means that at that transition point, that will have a solid dot at the transition, indicating that negative 1 belongs to that part of the graph, that piece of the graph. This will have an open one, meaning that negative 1 does not belong to that, but everything up to that point would. Okay, so now these are both in vertex form. So one strategy could be to think about, okay, well, where is the vertex of each? And, does that fall within the restricted domain of the definition? So, like, for example, the vertex here of this first one, and maybe we'll go this brighter blue. So for this first one here, the vertex is 1, comma 2. So that clearly, when x is 1, that's greater than negative 1. So 1, comma 2 would be the vertex of this particular parabola. It is a negative, so it's opening down, and its increase is a 1. So when I go over 1, 1 squared is 1, so I know it's going to go here and here. And then when I go over 2, 1, 2, it's going to go down 4. So, or I could think about putting in negative 1. Negative 1 minus 1 is negative 2 squared is 4, we said. So, but then negative 4 plus 2, so that's a negative 2 value. So 1, 2. But that is going to be an open dot, because that value is negative 1, and when x is negative 1, it technically doesn't belong here to this part of the function. So that's negative 1, comma, we said negative 2, but there's the rest of the parabola. So I'm going to fill that in, and then, so it goes on forever in that direction. So the blue represents, hey, if x were greater than -1, this is the shape. And, you could, if you wanted to highlight this too, you could. So basically, all of the x's that are here on this side, right, this side of the graph, that's where like x equals -1 and greater, all the x's on this side have to behave following that function, which we just graphed. Now, if your x's are less than -1, so like now you're on this green side. Oops, I thought I clicked that. This green side, there it is, like, right? So if you're on this side of the divide of -1, which was picked, that means you're going to follow this function. And notice its vertex is at -3, -6. So go back to my pen, and I'll go to maybe red, which I like that to kind of contrast it. So at -1, it's going to go down. Oh, sorry. At -3, it's at -6. So 1, 2, oops, pen. Undo that. My bad. Pen, red color. There we go. 1, 2, 3, and then -6. So 1, 2, 3, 4, 5, 6. So here's the vertex. It is opening up. And so then again, thinking about, going 1 to the right, up 1 squared. 1 squared is 1. 2 would be up 4, over 2 up 4, over 2 up 4. Or thinking about putting in -1, the transition point. -1 plus 3 is 2. 2 squared is 4. And then 4 minus 6 is -2. So it's kind of interesting that a -1, 2 for the red function is actually a filled in dot, but -1, 2 was an open dot on the blue function. And the thing I want you to realize is that not every piecewise function is going to line up so cleanly, right? So, because we had this piece, if I can pull it. Oh, maybe not. Ah, there it is. Right, we have this piece and it's lined up perfectly with this piece right here. It may not always do that. This transition point might have a jump in it. And actually, it's kind of interesting because the other class I teach is calculus, and that's exactly what we're studying, is if there are jumps or discontinuities in graphs that do not make them continuous. So, okay. So, but that's something to look forward to for next year, right? But again, just some reminders of completing the square. An absolute necessity. You absolutely need to know how to complete the square. And as we start solving quadratics, by completing the square, I think, is even more useful than the quadratic formula. Okay, so let me know if you have any questions or if I made any mistakes.